Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about gases. So we're going to elaborate on the characteristics of gases. We're going to talk about pressure in a little bit of detail on how we measure pressure, as well as we're going to talk about the named gas laws that exist. So let's get into this video. So the first thing we're going to talk about are the general characteristics of gases. All gases have very similar physical properties in most cases. They're typically going to be nonmetals. You're not going to have metal vapor floating around the room at room temperature. So these are going to be nonmetals with very low molecular weights if they're in the form of compounds, as well as we've got monoatomic gas species. They're really cool because they can expand to fit their container. So they don't have a definite shape, nor do they have a definite volume. So whatever the container is, they're going to expand and fill that container. You can also go backwards. You can compress them really close together inside of an air compressor or an tire. So you can't really do that to solids or liquids, but you can compress a gas. Again, they've got really low density, so that's why our atmosphere is made of gases. They're going to rise the highest out of all the compounds around Earth. And if you've got two or more of them and they're mixed together, they're going to form homogeneous solutions. And if you need to remember that, you can go back to one of the previous videos to see what kind of solutions that we have. So now we're going to start talking about some gas laws where people have names. So they're going to be named gas laws. So each person is going to have a different contribution, and eventually we're going to come to this combined gas law. But the first person that we're going to talk about is Boyle's law. So Boyle's law is a pressure-volume relationship, and this is inversely related. If we had a sample and we compressed it to half of the volume, the pressure is going to double. So as one goes up, the other one's going to go down, and vice versa. So if we go to plot this on a graph, you're going to get a curved line. And typically we want to use straight lines in order to analyze some data. So if we take the inverse of pressure versus volume, we're going to get a straight line with the slope is equivalent to a constant because the slope is not going to change. So if we're trying to do some math with this, we're going to have pressure times volume is equal to some constant, which is the slope. So any point along that slope, you might have pressure 1, volume 1 is equal to constant. Pressure 2, volume 2 is equal to the same constant. So you can set these equal to each other. And this leads us to our Boyle's law. P1 V1 is equivalent to P2 V2. The next guy on our list is called Charles. So we're going to talk about Charles' law, which is a volume temperature relationship. And again, you need to make sure you convert your temperatures to Kelvin, or else your calculations aren't going to come out correctly. So if we think about a balloon and we were to take this balloon and stick it in the freezer, the balloon is going to shrink. So as temperature goes down, the volume is going to go down. So this is a direct relationship. So if we were going to have a direct relationship, we're going to have volume is equal to a constant times temperature. And if we isolated our constant, it would be volume over temperature is equal to a constant. And this is directly related, so we are immediately going to get a straight line and our constant is going to be the slope. So if we were to take 2 points, V1 over T1 equals constant, and V2 over T2 is equal to the same constant, then that leads us to our Charles law. V1 over T1 is equal to V2 over T2. The next guy on the list is Gay-Lussac's law. So Gay-Lussac's law is a pressure-temperature relationship. And this is also directly related. If you had the idea of like your tires and now it's winter time, your tire pressure is going to go down when the temperature gets really low. So you're going to need to inflate your tires more in the winter time. So if the temperature is going down and causing the pressure to go down, this is again directly related. If pressure goes up, temperature is going to go up as well, or vice versa. So we're going to have a direct relationship. We go to plot this, we're immediately going to get a straight line with some constant equivalent to the slope. So P1 over T1 equals a constant. P2 over T2 equals a constant, and we can set them equal to each other. So Gay-Lussac's law mathematically is P1 over T1 equals P2 over T2. So now we've got all of these different gas laws. So we've got Boyle's law, Charles' law, and Gay-Lussac's law, and they all share one term with each other, either the pressure term, the temperature term, or the volume term. So we can combine all three of these different gas laws into one gas law called the combined gas law, where we've got P1 V1 over T1 equals a constant, P2 V2 over T2 equals a constant, and you can set them equal to each other. So we can use the combined gas law. If you forget one of these Gailes Law or you don't know the name of one, if you know something's being held constant, then you can just plug in a 1 for those values. So say we held temperature constant, and we can just plug 1s in for our temperature value, and you're left with Boyle's Law, P1V1 equals P2V2. Or if you wanted to hold volume constant, you just plug in 1s for the different volume terms, and you would have P1 over T1 equals P2 over T2, which is Gay-Lussac's law. So this is the use of combined gas law. It's just taking all three and combining them together. So the last guy we're going to talk about, you guys should already be familiar with from previous video dealing with stoichiometry, and this guy's name is Avogadro. And Avogadro focused on the idea of a mole. He also worked with a lot of gases. So Avogadro's law is a volume-molar relationship. So if we've got more moles going up, the volume should also go up. So this is a direct relationship. If we're at that special condition we just talked about, STP, standard temperature and pressure, which is 0 degrees Celsius, 273 Kelvin, and 1 atmosphere of pressure, then we get this special conversion factor, where 1 mole of any gas at STP is going to take up 22.4 liters. So if we had 2 moles of gas at STP, it would take up 44.8 liters. So it's this special easy conversion factor as long as we're at STP. And this applies to any gas. If you have 1 mole of helium, 1 mole of oxygen gas, 1 mole of neon, as long as it's at STP, all of them are going to take up the same volume. They'll have a different molar mass, so they're going to have a different mass within that 22.4 liter volume sample, but they're all going to have the same volume. So that brings us to our mathematical relationship again. V1 over N1 is equivalent to V2 over N2. So this is Avogadro's law mathematically. If you're not at STP, you can just use this direct proportionality. So there it is, you guys. There's the video on characteristics of gases, the idea of pressure and how we measure pressure, as well as the introduction of different named gas laws. So if you found this video useful, smash the like button, send it to your favorite fruit, send it to your favorite vegetable, and we'll see you in the next video.